Okay, so today we're starting Unit 7, which is called Thermochemistry. So, does anybody want to make a guess about what thermochemistry is going to involve? Yes. Okay, so let's talk about some of these things. Today is going to be very definition heavy, not a lot of math. And so this is a little bit of a deviation from what we normally do. I'm using my notes today, which I'd almost never do, so that I can remember to stay on task and on topic. I think that I can do this in 40 minutes. Okay, so heat is the most common form of energy that we experience or calculate or observe in chemical reactions. Energy. So I almost always abbreviate the word energy with a capital E. So just get used to that because I don't like writing out the word. Capital E is always in reference to energy. And so that's a universal abbreviation. What is energy? Energy is the capacity to do work. In order for work to be done in the scientific realm, work is almost always defined as work equals force times a distance. So if you've had physics, you've already experienced that that's how we define work. And so if you can push something. And so if I asked Joe to come up here and push my desk, he could push it with all of his strength, but he wouldn't be able to move it, hopefully, because it's bolted to the ground. And that would be sad if he could move it. But if he doesn't move the desk a certain distance, no work is actually done. In the same way that you can do work by thinking in your mind, like that can be work. But in terms of like science, we define it as something has to be moved over a distance. In chemistry, the work that we almost always use is pressure times volume. And if you take AP Chemistry next year, you'll spend a little bit more time on this. Or if you take AP Physics, you'll spend more time on this. But that's how we define energy in the scientific sense, the capacity to do work. Okay, so then what is thermochemistry? It is the study of the heat and energy associated with chemical reactions. The study of heat and energy associated with chemical reactions. And so the very first day of this class, when I gave you the definition of what chemistry is, I said it is the study of matter, its properties, the changes it undergoes, and the energy associated with those changes. Now, finally, the last unit is where we're going to talk about that last part of the definition of chemistry itself, the energy associated with those changes. So today we're going to get a foundation in the terminology that we'll use in thermochemistry. But then also we'll talk about one tiny mathematical equation, and then we'll start talking about thermodynamic equilibrium and other ways that energy is associated with chemical reactions. Okay, so let's just make a distinction between the two main types of energy. There's kinetic energy, which is the energy of Energy of moving things. Energy of motion. Specifically in chemistry, we are going to be talking about the thermal energy of atoms, molecules, etc. Every single atom, every single molecule has a thermal energy. And the only time it doesn't, the only time matter, so that's any of your things that have mass, the only time matter has zero thermal energy is when you are at absolute zero. Which, remember from the gas laws unit, is at 0 Kelvin. That is the point when the motion of matter stops. So the definition of absolute zero is when there is no thermal energy.
Equals what?
Zero kelvins. It's when you're at 0 kelvins. That's not something that has been attainable for science. It's currently only a theoretical construct. We've gotten pretty close, but not close enough. The other type of energy is potential energy. Potential energy is the energy of position. And so we contrast potential and kinetic energy. Potential energy is what an object has when it has the potential to do something or the opportunity to do something, but isn't doing it yet. And so if an object is stationary, it would have all potential energy and no kinetic, which makes sense. It's stationary, it's not moving, so it wouldn't have kinetic energy. And when an object is moving, it doesn't have potential energy because it's using up that potential. The potential energy that we think of in chemistry is actually called chemical potential energy, and it is the energy that is stored in bonds between atoms, and when those bonds are broken, that energy is released. There is also electrostatic potential energy, and that is the energy of attraction. And so when you have two ions that are, I'm just going to write ions in parentheses. If you have two ions that are attracted to each other, like sodium and chloride, what these atoms experience is electrostatic potential energy. Similar, but not the same as chemical potential energy, because there really isn't a bond between these two substances. There's just an attraction that holds them together. Bonds are technically when electrons are shared. Okay, the first law of thermodynamics then is, so this is a new section, like after kinetic and potential. The first law of thermodynamics, you should already actually know. Somebody at some point, hopefully, praise God, in your science career has already told you that energy cannot be created or destroyed. Have they told you this? It can only be created. It can only be, what did I say, created? It can only be converted into different forms. So potential energy can be converted into kinetic energy. Kinetic energy can be converted into potential energy, but that energy has to go someplace. It can't just, cease to exist. The first rule of thermodynamics is actually capped because it has been disproven. But because the math is too complicated otherwise, we pretend that it's true. Okay, so now that we know that, let's talk a little bit about the difference between temperature and heat. So in regular life, we think about temperature as the way that we measure how hot or cold or something is, and to us, that tells us what the heat of a substance is. And that's a good thing in everyday life. And so if I said, Alexa, what temperature is it right now? 50. Oh. He's too quiet. I couldn't hear him. Okay, so if it's 51 degrees, that tells us that it is not cold, but not hot either. But to us Wisconsinites, it feels probably pretty nice. Okay, so let's talk about what the difference is then. Temperature is the average kinetic energy. And so I'm abbreviating this KE for kinetic energy. The average kinetic energy of all the particles in a substance. So when we ask Alexa and she says that it's 51 degrees outside, not all of the air particles, all of the air molecules have a temperature of 51. That's just the average. Heat is not the same thing as temperature. So we have to not really think about like temperature as being how hot or cold something is. Temperature is just a measure of how much energy the substance has. Heat is the flow of thermal energy from an object of high energy to an object of low energy. And I'm saying low energy, but I mean low thermal energy. Okay, so temperature is measuring the average kinetic energy of all the particles. How do we measure kinetic energy? Kinetic energy is always found by this formula, where m is the mass and v is the velocity. So really, kinetic energy then is a measure of how fast the molecules are moving, and that's it. Heat is always going to flow from areas of higher heat to areas of lower heat. And this is why it's not helpful when it's really hot for you to like open the refrigerator door and like feel like you're getting cooled off.
Wait, what's the equation?
That's 1/2 mv squared. You're never going to use this in this class. And so I just put this here for you. This is velocity. You don't have to write it down because we won't use it. So in other words, temperature is the average speed of all of the particles. So the higher the temperature, the faster the molecules are moving, provided they're the same mass. So heat is always going to flow from high to low. So when you open the fridge door and feel like you're getting cool, that's true. But that's because the hot air from you is leaving, or the heat from you is leaving to go into the refrigerator, which is bad for the things that you're trying to keep from spoiling. And so that might be like successful for a moment, but not for a sustained period. And your food will just go bad. Okay. Directionality of heat transfer always occurs from areas of high to low, and it continues until both substances have reached thermodynamic equilibrium. I want you to write this down. I want you to put like a little star by it because it's really important. But we will talk about this concept of thermodynamic equilibrium next time when we learn about calorimetry. Okay, so when you get your homework, there is going to be a question that asks you to explain the differences between temperature, heat, and thermal energy. So that means we need to really go back and define what thermal energy is. Thermal energy is the amount of energy stored in a substance that is available can't spell, can't write, to do chemical work. So temperature measures how fast molecules, like the average speed of molecules in a substance. Heat measures how energy will be transferred from one substance to the next. And thermal energy is the energy that's stored in a substance that allows it to do the things. The more thermal energy, the more potential something has to do chemical work. So maybe put a star by this, like these three colors, the orange, the red, the green. I don't know what color you wrote them in your notebook, it doesn't matter. But that's the answer to question number 2 on your homework. All right, let's talk about a couple of other definitions and the energy diagram. There are 2 types of thermal processes in, hey, I'm going to sound like Father Dog, in life. Next time he gives a homily, count how many times he says the phrase in life, because it's one of his favorite things to say when he doesn't know what next to say. So there are 2 types of thermal processes. You know these definitions. The first is called exothermic. Exo means like outer or like to the outside. Exothermic means that you have a process, so a reaction, a change, that releases heat energy or heat into the surroundings. A lot of times you can identify an exothermic process by something that feels hot to you. And so if you use, have you ever used like the hand warmer packets?
Yeah.
Do you know how they work? They don't work until you open them. And when you shake them, what you're doing is exposing the chemicals that are inside the little packet to the air, and that reaction produces heat. And so you feel the heat because you're the surroundings, and that chemistry that's happening in the little packet when you're shaking it, or like after you shake it up, that reaction produces heat. So heat is a product, and it feels hot to your hand because you are the surroundings. So in a reaction, in a chemical reaction, you would have a reactant plus or yields your products, and then heat is one of those products. Now I know because I once helped a kid on their homework for middle school, and I know that you've made these before. This is called an energy diagram. And so your reactants always are going to be pointing like with an arrow toward your products. In an exothermic reaction, your reactants have more energy than your products do. And so where did the energy go? It goes to the surroundings. This to you, if you are the surroundings, feels hot because you're the surroundings, you've absorbed the heat. This is what an exothermic energy diagram looks like. Now the opposite is also true. Does anybody remember what it's called, like the other kind of process? Endothermic. Endothermic means that it's a process that requires energy in order for it to work. So if you put, anybody make ramen on the stove? Anybody make mac and cheese on the stove? Or in the microwave? You're adding heat to the water to make it boil. And so because of that, that's an endothermic process. If you have to add energy to make something happen, you are experiencing an endothermic process. Okay, so in the case of your energy diagram then, what will it look like? Your reactants will have less energy than your products because something from outside the system had to come and add energy to it. These are the processes that a lot of times I'm just going to write it as energy because I don't want to confuse us. Energy added. A lot of times it feels cold to us. So if you put an ice cube in your hand, obviously it's cold, right? What would happen to it over time if you just let the ice cube sit in your hand? What would happen? It'll melt and it'll feel cold to you. Eventually it'll start to feel hot because that's how your body reacts to extreme cold. It makes it feel hot. And so it's because the nerve endings get like hurty over time. Like they get so cold they hurt, and then it feels like they're burning because they're like freezer burned, kind of. That's why a lot of times, yes, you may. If somebody freezes to death, okay, so if you're driving a car and you get stuck in the snow, don't ever leave your vehicle. Like if you're not sure that somebody can come, if you're in the middle of nowhere, don't leave your vehicle because the heat is trapped in there and it'll stay pretty well trapped in there. Sometimes people get out and start to walk and think that they can make it and then they freeze to death. One of the symptoms of hypothermia is that you start to get really hot feeling, and so they'll take their clothes off because they feel so hot, but it's really because they're so cold. Really? It is. It's actually one of the most horrible ways to die. Okay, so that's your endothermic process and your energy diagram. Now, before I get to the one little bit of math that we're going to do today, let's talk about one more definition. I really wanted to do this in black. And that's the word enthalpy. Enthalpy. There are two words in thermodynamics that both start with E besides energy. One's called entropy, which we will not be talking about, and this one is called enthalpy, and they both are different types of measuring energy. Mason, were you going to ask me a question? Okay. Enthalpy is not abbreviated E because energy has the abbreviation E. Enthalpy is abbreviated capital H. Isn't that great? So where does the H come from? It comes from like here inside its name, but we know that enthalpy is, let's see, how do I describe this? The term we give heat associated with a chemical reaction. So how dare we actually use a word that means something in English? Let's make up a new word in chemistry land that nobody else uses except us to confuse the crap out of people. Great days. So when we use the word enthalpy, we're really talking about heat associated with the chemical reaction. And so if I said to you, the combustion of a fuel releases this much enthalpy, what I'm really saying is it produces this much heat. And so those are the English words. Produces heat, releases enthalpy is how you say that in chemistry. And so capital H, while the H does come from inside the word, what it really stands for is heat. Or that's how you can remember it. Okay, so that's all we have for definitions, except for the definitions in, I'm got ahead of myself. In this equation, this is a Q. So E stands for energy, and in this case specifically the internal energy of a system. If you take more and more chemistry when you get to college, you'll learn that internal energy does not have the abbreviation E. I'm using that because it makes more sense. Internal energy is abbreviated U. I know that that's true, but I'm choosing to use it here for your sanity. Q is the abbreviation for heat. But Ms. Bishop, you just said that enthalpy is heat. That's true. So the Q in this case refers to the enthalpy. Why is it given Q, especially because Q has other abbreviations? It's because we're not specifically talking always about a chemical reaction when we're talking about a process. So H specifically refers to the heat associated with a given chemical reaction. But not all things that produce heat are chemistry. And so therefore Q here applies to this more, it's like a more broad definition of heat. Yes, Mason?
So in that case, this wouldn't apply to a chemical reaction?
It would.
And then if you do that, can you put H in there?
You would. Yes. I know it's very confusing. Don't worry, I will be very clear with you what I mean and when to use this equation. The W here stands for work. And you'll always see that word work associated with the W. So that one I think is a little more clear. The problems that use this mathematical equation are not hard. And I think that I did a pretty good job of writing them with clear enough language that you can make sense of it. However, this is where things get a little bit tricky. It's important, so I'm going to use rainbow pen. So this equation is really simple looking, right? It's just thing plus thing, right?
Yeah.
Easy, but not so much. You must determine the sign of Q and W in every problem. I will help you do that, but it's important that you are deciding whether or not heat is leaving or entering a system. So let me explain to you how the sign convention works. If this is your system, if heat is leaving, if Q leaves, its sign is negative. If work is done on the surroundings, work is negative. So if it says, if your terminology says done on, I'm going to put it over here, done on surroundings, your sign is negative, because it means that the energy has left the system and gone to do work elsewhere. The opposite is true if heat is, oops, that's not the opposite. If heat is entering into the system, its sign is positive. If work is done on the system, the sign is positive. So you would see words like done on the system or added to the system. So you have to be very careful about the wording and you have to remember that if it's not in the system, it's part of the surroundings. You as a chemist are observers of reactions. You are almost never the system. You are almost always the surroundings. Unless you're doing tests on yourself, and that's just weird. It's weird if you're a chemist. Okay, so one last thing, and that's the unit for energy is the joule. Not that kind of joule, Kaden. I thought they went out of business.
Oh.
I think they just were bought by someone else.
That probably is true. They probably just bought for market share. Joule is the name of a scientist, Joule Thomson, and so that's where we get that name from. You might have to do some unit conversions, but like these are the easiest unit conversions you could imagine. Let me see. What did I have here? I didn't even give you any unit conversions. So if you have 1 kilojoule, how many joules do you have? Not Juco.
A lot more.
How many though?
1,000?
Thank you. So that's how you would convert between joules and kilojoules. When you're doing this math, you have to make sure that your unit is the same for both things. So be cautious about that. The SI unit for energy is the joule, but the joule is kind of a big number, God bless you. And so we often use kilojoules as our unit of measuring, because otherwise we'd have like 200,000 joules. But the SI unit is properly the joule. All right, I'm going to give you your homework.
Can I go to that?
You may. And we'll do a couple of problems on here. You're only going to be able to do
lost about
halfway through page 2. Oh, interesting.
Hey, you want us to write everything out like...
I'll explain that in a moment. Okay, let me explain to you what I'm expecting for answers. It's the first time in a very long time that I'm asking you for like word answers on a homework. Miss Bishop does not want complete sentences. However, she does want things to be spelled properly and for you to use your full brain when writing these answers. So if I say explain the difference between kinetic and potential energy, write something like KE equals energy of motion. PE equals energy of position. That's all I want. I don't need a full sentence. I don't need a full paragraph. Brevity is the soul of wit, especially if you're a chemist. I don't want to read your stuff, but I do want to know that you are using your brain noodle.
Wait, is potential energy PE?
It is. You have the answer for number 2 in your notes. I told you where to mark that. Number 3 says use an energy diagram to explain your answer. So, and it says the word endothermic. I'm going to go back here to my notes and plop that stuff down in my little space there for my thing. For number 4, you can write the answer either exo or endo, and that's all I need. For number 6, your first couple of questions, your first couple of parts of that, I give you the sign for each of the things. But on page 2, you need to decide what the sign for each of those substances is. Your equation is going to be the same for all of them. It'll always be E equals Q plus W. Okay, so let's look at number 2D. So the first one on page 2. It says that a gas absorbs 45 kilojoules of heat and does 29 kilojoules of work. Okay, so here's my formula. If a gas absorbs 45 kilojoules of heat, what do you think the sign is? Raise your hand if you think it's positive. Raise your hand if you think it's negative. The positives win. If it's absorbing heat, it means that it is coming into the system. Remember, we said that if heat goes into the system or is done on the system, that's positive. Okay, but then it says it does 29 kilojoules of work. A system cannot do work on itself. So that means that it has to do external work. Is that positive or negative? Negative. So that's the choice you have to make for all these questions. You have to decide if you've got a positive or a negative for each one of those. Yes, right. My hair did that. So the math for this is 16?
Yeah.
Unit is kilojoules.
I thought you did.
And that's it. Now, this is an endothermic process. Your substance is endothermic. Do I ask that? Oh, I do. Oh, good. Well, I'm glad that I wrote this. If your answer is positive, it's endothermic. And that makes sense to us because if we have to add stuff, if we have to add energy to our system, that's what we showed here on the endothermic energy diagram. So if we're adding energy, which is what we have when we have a positive sign, that's an endothermic process. If this were to be negative 16, then your answer would be exothermic. You can just write the word endo. Does that make sense? Please only do up through number 6. When you get to number 7, you won't know how to do those. I will teach you that next time.
If it says the work done on it, it's the same thing.
If work is done on the system, that would be, it would be positive. I highly recommend getting these questions checked because it's really easy to, like sometimes you can get your mind in a rabbit hole when you're thinking about these things and it becomes a little more difficult. So get your number 6s checked at least.